Sorry about that. My iPad died. I suppose that was a good enough time to cut it and go to part 2. So we left off talking about the normal force being 3.2 newtons, and then we were looking at how to find the maximum height that the block would achieve after it had left this little roller coaster. And the final velocity at the maximum height is going to be 0. So all you see is the minus the initial velocity. Now, because it's talking about the maximum height, all you care about is the velocity in the y direction, which is why you take 4 times the sine of 30 degrees, because that's going to give you the part of the velocity that's making it go up instead of over. So you plug those numbers in and you end up with an answer of 0.7 meters. Alright, part E. The only thing that's different about part E from part A, okay, so there's part A. So you got potential energy at the top is equal to kinetic plus potential at the bottom. Well, now you've got potential energy at the top is equal to potential plus kinetic plus a little bit of work that was lost. So if you solve for work, you end up with this equation. Plugging in your numbers, you have an answer of 0.67 joules. Now, typically work would be written as a negative number because it is taking energy from the system. But that's how much work was done. I'm sorry, that's how much energy was lost due to work. Okay, here's the conservation of momentum problem. You've got a big gun that shoots a bullet at an angle of 40 degrees, and there's your general formula for momentum, just P equals mv. Well, the momentum of the shell in the x direction is all you really care about here, because that's what's going to cause the gun to kick backwards and recoil. So you take the momentum of the shell, which is 30 times 300, I apologize, that's a typo, and multiply it by the cosine of 40 degrees, and so this number right here is going to be wrong. I'm sorry, it's very late and I've been working on this for a long time, so I believe this number is supposed to be 300 and not 3,000, which would mean this is 689 instead of 6,894, which would mean that this would be 0.46 instead of 4.6, okay? But here's your momentum of the shell in the x direction, which means that your momentum of the gun in the negative x direction is basically the same. So it's the momentum of the gun plus the momentum of the shell. They have to equal 0 because the momentum before the gun was fired is 0. So if you solve for the velocity of the gun, you end up with just the momentum divided by the mass and you get the velocity. But again, check that number. I think it's supposed to be 300. My mistake. The next one here is the torque around the bar on 2 pivot points. So they tell you to use the point on the left here, which I called point 1. So there's point 1. Point 2 is halfway down the middle. That's where the force of gravity is acting. Point 3 is the other pivot point. So there's the force diagrams, and so you got 2 normal forces and you got the force of gravity. Now the torque equation is just force times the distance away from the pivot that the force is acting. Since this is the pivot, there is no torque about the first due to the first normal force, which is right here. Force of gravity is halfway, so it's 3 meters to the right of the pivot point, which is why I did mass times 9.8 to get the force of gravity, and then I multiplied it by 3 meters because that's how far away it was. So you get a torque from the force of gravity of 353, which means that the other torque produced by this guy right here has to be the opposite of that. Positive and negative doesn't matter. I just called clockwise positive, which means this torque is negative. The sum of the forces and the sum of the torques have to be 0 for equilibrium to be achieved. So there's your 2 equations. And I'm just going to zoom in on the math and you can check it and see what I got there. But your answer for the forces of gravity and the 2 normal forces, there's the force of gravity. And there's the normal force due to the pivot point on the right, and the pivot point on the left has a force of gravity that's a little bit bigger, 67.2 newtons versus 50.4 newtons. Weight is 117.6. Alright, we are almost done. Okay, number 22 is what we call an Atwood's machine, and I was solving it and double checking my answers in the back of the book, which is what you should be doing, and I realized that their solution was pretty good. So I drew the force diagrams. They have these as well, but they pretty much show you what to do in the back of the book. So go to section A21 in the back of your book and you should be able to check those out. 23 talks about, is there a torque on the disk? Yes. The system is basically just the big disk and the little disk. So the initial angular momentum, you just take the moment of inertia of the big disk, which is just mr squared over 2, and then you multiply it by its angular velocity. Plugging in the numbers, you get 2,000 kilogram meters per second. Okay? These right here show you the moment of inertia for the big disk and then the little disk. Notice how much smaller the moment of inertia is for the little disk, 3.5. So the angular momentum equation is right here now for part D. It has to be conserved. So because they're now stuck together, this is like an inelastic collision. So you just add their two moments of inertia together, multiplied by the new angular velocity. That whole total is still got to be equal to 2,000. So you set 2,000 equal to that, plug in what you know, 40 for the big disk, 3.5 is the moment of inertia for the little disk, times some angular velocity you don't know. So if you add those together, you get 43.5. This is what D was asking you for. And then E was just asking you to solve, so you get an angular velocity of 46 radians per second. Last page. Okay, the thing about having more than one spring attached to a mass, particularly if the springs are equal, they just add together. So instead of having 3 springs with one spring constant of 40 newtons per meter, you just multiply that by 3 and it acts like one spring that's 3 times as stiff. So the new spring constant is 120 newtons per meter. When you plug that into the period of a spring formula, which is right there, there's your numbers, there's your period. So 2.6 seconds. Okay, 25 is a pendulum. You've got to do this whole thing right here to figure out, first of all, how you would find the length of this thing here on Earth, okay, which when you plug in the numbers you get a length of 1.55 meters. And then now that you know the length, now that you can go to the moon, where gravity is only 1.6 meters per second squared, and if you plug in your numbers you get a much longer period, which is 6.18 seconds. 26, that V equals lambda F there is the basic wave speed equation. So you're looking for wavelength, which is just speed divided by the frequency. Well, they don't give you the speed, but they tell you that it goes 0.3 meters in a time of 3.5 seconds. So that's the speed. Divide those two to get the speed, and then divide it by the frequency of 2.3 and you get a wavelength of 0.04 meters. The last one was talking about the time it would take for a beam of light. I think it's a radio wave. It doesn't matter because they all travel at the same speed of 3 times 10 to the 8th meters per second. But you don't care about the speed of light, you care about how long it's going to take to get from us to Mars or vice versa. So you basically have to take the distance between the two and divide it by the speed of light. Well, the way that you get the distance, they tell you to use the average orbital radius and just find the difference between those two. So here's the average orbital radius of Mars, 2.28 times 10 to the 11th meters minus 1.5, that's Earth, times 10 to the 11th meters. So the distance between us when we're closest together is 0.78 times 10 to the 11th meters. Well, if you put that number on top, right here, and you divide it by the speed of light, which is 3 times 10 to the 8th, you get about 260 seconds. So that's how fast or how long any light signal traveling either from Mars to us or from us to Mars would take to arrive. And that should be the end of the final review. Good luck, and I will see you Tuesday.